So what we will be doing now is consider a quasi-Keplerian accretion disk of this kind, right? And consider the mass and momentum conservation equation. What else, right? I mean, there are only these two things, and try to figure out what the structure of such an accretion disk will look like. Okay. Now, before doing that, we have to do a little bit of geometry, and that is we are going to be talking about a thin accretion disk. Okay. A thin accretion disk. In other words, one which looks like this. Okay. What does the word thin mean to you? Well, it looks thin. Okay. What do you mean by that? Really, the vertical dimensions, okay, it looks like a thin plate, right? So the vertical dimensions are very small in comparison to, say, the radial dimensions, right? So this is what we are talking about, and the appropriate geometry. I mean, one should always, when one was talking about spherical accretion, the the appropriate geometry to the appropriate coordinate system to adopt was a spherical coordinate system. In this case, turns out that the cylindrical coordinate system is much more convenient. A cylindrical coordinate system would be one where, for instance, you had the standard Cartesian axes x, y, and z like this, right? And a cylindrical coordinate system would be one where you would have an r coordinate in the xy plane, okay, it's lying in the xy plane, and a phi coordinate which would be like this, right, a phi coordinate which would be like this, and a z coordinate which is just along the z axis. So essentially you would have an r hat, phi hat, and z hat. So this is the cylindrical coordinate system within which cylindrical coordinate system. This is the coordinate system in which we are working. Okay, and we will first consider the mass conservation equation. Okay, so you remember what the mass conservation equation looked like. In general, the mass conservation equation looked like d over dt of rho plus gradient of rho v was equal to 0. This is how it's written in general, in a coordinate system free manner, where the divergence operator assumes an appropriate form in the appropriate coordinate system, right? You have, for instance, in a Cartesian coordinate system, this would be just x hat d over dx, y hat d over dy, so on and so forth. For a cylindrical coordinate system, okay, in a cylindrical coordinate system which looks like this, this essentially would look like d over dt plus 1 over, and now I will be writing capital R in place of the capital R essentially means this. Okay, so maybe I should actually erase this here and write a capital R here just to be consistent. Okay, it's also good to write it this way because I distinguish between the spherical R and the cylindrical R that I'm using. Remember, the spherical R would be pointing somewhat like this, whereas the cylindrical R is pointing outwards and it's always in the xy plane. Okay, and so in a cylindrical coordinate system, the mass conservation equation would look like this: 1 over r this and this are the same. All right, now let me integrate this equation. Let me write this down once again. Okay, this is the mass conservation equation I want to Okay, right. So now let me write this, let me write this down because I'm going to integrate it vertically. So let me write it down once again just to be a little safe so that we don't make any unnecessary mistakes. What is this v sub r? This is the all important radial velocity. Okay, the velocity at which material is accreting in a radial manner. In a perfectly planar accretion disk, this term simply would not be there. V sub r would be 0. There would be no accretion. Okay, mass conservation would simply be this. That is it. Okay, whereas in this case, we assume a finite v sub r, and we will see what the conditions of v sub r would be. So I integrate this vertically, right? So I integrate this vertically to write like this. In the vertical direction would simply mean in the z direction. Okay, I'm assuming that the accretion disk is so thin that there is no appreciable variation in the z direction. Okay, we will come to that, but for the time being I integrate this vertically to get what's called the surface density. So I'm assuming that I can interchange the integration and differentiation. So I'm keeping the d over dt outside and I'm integrating like this. I'm formally writing from minus infinity to infinity. The z extends from minus infinity to infinity, but of course it extends only over a finite thickness. So the only contribution comes from that finite thickness. The rest of it just goes to 0. And now what I'm going to do here is 1 over r d over dr, and the r comes outside. This r I take outside, and I allow the rho and the v sub r to be functions of z. So I can write rho. So this is essentially a vertically integrated version of this. Okay, now if the assumption is that there is no vertical structure. In other words, this rho dz essentially becomes rho times h, where h is the half thickness of the disk. Okay, so it actually becomes rho times 2h, where h, the disk, looks like this. So this would be the vertical plane, and the half thickness would be h. Okay, so the vertically integrated version of this essentially becomes, so I have a d over dt, right, rho times 2h. So this integration, so because there is no vertical structure, I can pull the rho out, right, and the integration of dz from minus infinity to infinity essentially becomes 2h, because there's nothing else. This is the accretion disk, right, and there's nothing here or there, right. So this essentially becomes rho times 2h plus 1 over r d over dr r, and I pull both of these, the rho and the Vr. Here formally they are allowed to be functions of z. Okay, whereas if I assume that there is no disk structure, I can pull both of these out, and this becomes r times Vr times rho times, okay, I forgot to write a minus infinity to infinity here. So this also becomes 2h. This is equal to 0. Now we're almost there, right? And now what happens is I get, now I consider in steady state, and you remember what we mean by steady state, right? I mean, all across. Steady state simply means that according to the observer in the lab, there is no time variation. In other words, the partial d partial t goes to 0. So in this equation, I simply throw away this entire term and I only worry about this term, right? So if I do this and I integrate over r, right, so this essentially yields r equals some constant, which the constant can be anything I choose to write this as minus m dot over 4 pi. Okay. So, this is simply an integration of this equation, an integration of just this term of the equation. I integrate this, and so I just solve this differential equation, and this is of course the all important accretion rate, right? And so essentially I can write the accretion rate as you will see in accretion rate, our entire discussion of accretion disks, the accretion rate plays a very, very important role. Okay, so the accretion rate is essentially, this is essentially the same equation as this. M dot is equal to minus, and the minus is important, I'll tell you why, 2 pi r rho Vr times 2h. Now, so this is a very important equation, the accretion rate equation, right? And so what does this really represent? Consider a disk, a sort of a, like this, like that, and there's a central object, and so that would be the axis. And so what this is essentially saying is that, you see, what is the surface area of the side of the disk? That would be 2 pi r, where this would be r, of course. Okay, so it would be 2 pi r times 2h, 2 pi r times 2h, right? So that's the area, and the area times the density, the mass density, times the accretion velocity, obviously gives you grams per second. So that is essentially what this equation is saying. Okay, so you are essentially accreting in this kind of a thin disk geometry, and that's what this is saying. And the minus simply arises from the fact that the V sub r as such is pointing outwards, whereas the V sub r is inwards. You are talking about accretion. So the V sub r intrinsically has a negative sign, and that cancels this negative sign, and you get a positive accretion rate. Okay, so the mass conservation equation, just to emphasize, the mass conservation equation is just m dot equals minus 2. This is the same thing that we wrote down on the previous slide, no different. Okay, so we're done with our discussion of mass conservation, right? So we're done with that. And now let us look at the momentum conservation equation, right? So, so the momentum conservation equation, in general, we look at the Euler equation. In other words, we neglect viscosity, except of course for yes and no. For the time being, let us just proceed with this. The Euler equation generally is given by rho like that. This is a nabla minus gradient of pressure plus the all important body forces term. This is the version of the Euler equation that we've been seeing so far, right? And in this case, what will happen is we will have three different versions, three different components of the Euler equation. We will consider of the Euler equation, we will consider the vertical component, which is essentially the z hat component, right? And we will consider the radial component, which is the r hat component, and we will consider the azimuthal component. We will consider these three components of the Euler equation separately. It's important. Okay, right. So let us now consider first the vertical component of the Euler equation. Let's see how that looks like. And the vertical component of the Euler equation, of the momentum equation, the vertical component looks like 1 over rho dp dz. So you only have the pressure gradient term, and this is equal to d over dz. I will explain what these terms are in a minute, but before that I just want to say that this assumes that you look here, I'm considering, well, first of all, it's steady state, therefore this term is completely gone, right? And the other thing is, I'm assuming that there are no velocities at all. There are no vertically directed velocities. Okay. In the vertical direction, you only have a competition between the pressure gradient and the gravity. That's what this is. You have the pressure gradient and gravity. That is all, So this entire thing is essentially the minus rho times small g. Okay. So what this is assuming is that no vertical motions, i.e. Vz is 0, and it also, of course, steady state. These are the two important assumptions that go in. d over dt goes to 0. Okay. So these are the two important assumptions. Okay. So you see, we had written down the vertical structure, the vertical component of the momentum equation as this, and on the right hand side is essentially the gravity term. This is not just gm over r squared plus z squared. It takes into account the fact that you have the central object and you are at a certain distance r from here and at a certain height z. So you are really considering this. This takes into account the fact that the gravitational attraction is not simply along the radial direction, is actually along this direction. That's what this is all about. But at the same time, having done that, we then recognize that for a thin disk, z is much smaller than r, right? So this essentially becomes 1 over rho approximately, okay, is equal to minus gm z over r cubed. Where does that come from? You pull out an r, okay, you write 1 over z squared over r squared, and then you do a binomial expansion, and the fact that the z over r is a small parameter, right, and so this simplifies to this. Okay, all right, and next what we do is we say, so what we've done is we have come to a stage where we've written 1 over rho. Sometimes I write it as a capital P, sometimes I write it as small p. It's all the same, there is no difference. Write this. Now we do a horrible thing, which is also a very practical thing. Okay. We've seen the spirit of doing things earlier in the course. So what we do is we say, wherever we see a d over dz, we replace this as 1 over h, right? That's because we really have no vertical structure. Okay, so a d over dz can be replaced by a 1 over h. Okay, and we also replace this z here as approximately h. So, and we also say z is approximately h. So in this spirit of approximation, we can write the vertical momentum equation essentially becomes P equals gm rho h squared over r cubed. And not to despair, this will all become much simpler as we go along, right? So let me go to the next slide and reproduce this. What we have written is that we have simplified the vertical component of the momentum equation to look like this. And just to emphasize, how did we get here? We took the vertical component of the momentum equation, right? Actually, strictly speaking, it's this one. We made the assumption that we have a thin disk, so z is much less than r. So I do a binomial expansion in the small parameter z over r, and that gives me this. And I'm still not satisfied. I say I really don't want this partial differentiations. I would just write, d over dz is something like 1 over h. And here, in place of the z, I just replace it with h. And that gives me this. That gives me this. Okay. Now what I'm going to do is I'm going to say that we have a well-known relationship between p and rho, right? We are the sound speed, right? So I'm going to write p is something like rho cs squared. You agree with this? And now we are back to writing the sound speed as c sub s and not a, as we used to do in spherical accretion. It's always, I hope you're able to keep up, with these changes of notation. They're fairly transparent. Okay. Now, if we substitute this as, if we write this as equal to rho c sub s squared, then I get a ready expression for the height. Okay, the height of the thin disk is essentially equal to c sub s square root of r over gm times r. And we've seen this before. We've seen this quantity square root of r over gm. You remember, right? This is essentially 1 over the Keplerian velocity. We've seen this before. V phi, right? So V phi is equal to square root of gm over r. We've seen this. So using that here, what we find is that this is essentially equal to, the Cs is already there, Cs times V phi, where V phi is a Keplerian velocity, times r. In other words, I would write, the h over r is nothing but Cs over V phi, and this is such an important relation that I will write it on a separate slide. In other words, h over r is equal to Cs over V phi. So this is a measure of how thin the disk is, the quantity h over r. Okay, if h over r is small, that means the disk is small, and that has a certain demand on. Okay, so the other thing, of course, is we are assuming that this is indeed V phi. In other words, the disk is indeed quasi-Keplerian. So here, what we are implicitly saying is that V phi is very nearly Keplerian. So this is where we make the assumption of a quasi-Keplerian accretion disk. Okay, right. So here, what does it mean? So what would the h over r, if you foresaw the fact that the disk is thin? In other words, if h is, it means that V phi has to be, right? In other words, the azimuthal Mach number, which is defined as V phi over Cs, is very supersonic, right? So if you have a thin disk, it automatically assumes that the azimuthal Mach number is much larger than 1. Okay, and in a quasi-Keplerian disk, of course, the whole assumption of quasi-Keplerianity is that Vr is much less than V phi. So the radial Mach number is much less than 1. In fact, Vr is almost 0 in comparison to V phi. In fact, we have actually assumed that V phi is exactly equal to Keplerian. If that's the case, if V phi is exactly Keplerian, we have seen earlier that Vr is technically 0. So, V phi is not, although we call this V phi, it's not exactly Keplerian. There can be some departures from Keplerian value, which gives rise to a small but finite radial velocity. But at any rate, the radial velocity is much smaller than the azimuthal velocity, and the azimuthal velocity is highly supersonic if the disk is thin. And you can see that right from here. A thin disk automatically implies a supersonic azimuthal velocity. Okay, all right. So, and of course, we have, in writing this as a momentum equation, we have we have assumed that there are no vertical motions. So, Vz is equal to 0. So, this is one important part. The next thing, so what we've done is we have derived a very important thing from the vertical component of the momentum equation. Now, let us turn our attention to the radial component of the momentum equation. Remember, we started out by saying that we will split up the momentum equation. We will consider the vertical part, the radial part, and the azimuthal part all separately. So, now we consider the radial component of the momentum equation, which in cylindrical coordinates looks like this. Okay, this would be the u dot grad u term, right? Both of these taken together, and then you have the pressure gradient term, of course, except now the pressure gradient, we are talking about the pressure gradient in the radial direction, right? And then of course the gravity term, and we don't have to worry about the square root of r squared plus z squared. We are staying on the equatorial plane, therefore we only have to worry about this. Now, you immediately realize that we have written a VR here. Okay, this is assuming that there is a small but finite VR. Okay, now if the azimuthal velocity is Keplerian, right, we know that the second and the last terms in the equation, these two cancel each other. These two are exactly the same. This is equal to this if the azimuthal velocity is Keplerian, right. So, this term and this term exactly cancel each other for Keplerian V phi. Okay, right. And the pressure gradient term can be neglected. Why? You see, the 1 over rho dp dr is something like Cs squared over r, right? And because the p over rho dp d rho, p over rho roughly equal to Cs squared, and then the d over dr is roughly 1 over r. Okay, and this we know is much smaller than gm over r squared, because gm over r would be v phi squared. Okay, so this would be essentially v phi. So this becomes gm over r squared. This is simply this follows from here. This follows from this fact. Okay, so therefore the pressure gradient term can also be neglected, right? Therefore, so essentially the pressure gradient term is neglected, right? And the VR is small but finite. Okay, but since it's very small in comparison with the other terms, it can essentially be neglected, right? And so we are left with the inescapable conclusion that minus v phi squared over r is equal to gm over r squared. Okay, and so not minus v phi squared over r, v phi squared over r is equal to gm over r squared. In other words, the v phi is Keplerian. In fairness, this was something that we already knew, okay, and so essentially, in other words, we know that we had already assumed that the rotation was quasi-Keplerian. So therefore, the quasi-Keplerian assumption essentially obviates the need for an explicit radial momentum equation. If you assume quasi-Keplerianity, then you immediately say that this and that balance each other, but of course you have to realize that the VR is very small, and you have to justify the neglect of the 1 over rho dpdr, and the neglect of the 1 over rho dpdr comes from the fact that the CS is much larger than V phi, and that came from the vertical momentum equation. Okay, so at any rate, we have already considering quasi-Keplerian accretion disks to begin with, and therefore we find that that is what the radial momentum equation is telling you in any case, so we can forget about that. No need to worry anymore about the radial momentum equation. Now, the azimuthal component, this is a very important component, and the azimuthal component of the momentum equation, this involves viscosity. Okay, why is that? Well, you see, suppose you were looking top down, and we will not write down the equation right at the moment, but suppose we were looking top down on the accretion disk, right? So you have in one picture you have the central object here and an accretion disk here, which looks somewhat like this with a finite thickness, right? And matter is swirling round and round in a highly supersonic manner, and at the same time there is also very slow inward drift, very slow inward drift. Okay, now suppose I looked top down. I looked at this accretion disk from the top. Okay, what would I see? I would see orbits like this, yeah. And what does a V phi look like? The V phi goes as square root of gm over r, isn't it? So the essentially matter is the V phi here at larger radii is smaller, and the V phi at smaller radii is larger. You agree? So the length of the vectors, maybe I should draw this a little better. So the length of the vectors are such that at smaller radii, because the r is in the denominator, at smaller radii matter is swirling around faster than it does at larger radii. Now what is this telling us? This is telling us that this entire thing points to the fact that there is a velocity shear. The fact that you have a smaller velocity there and a larger velocity here. Okay, this is nothing but shear. You can always transform to a frame, to a rotating frame, where I can draw this like this. I have an in between layer at rest, and on one side of the layer the velocity is going up that way, and on another side of the layer the velocity is coming this way. So these would be the V phis. Okay, and this is exactly what a shear flow is. Okay, so what happens now? Now the reason I said viscosity is important is because it's exactly in this kind of situation that you think about, is exactly in this kind of a situation where you encounter shear that you start thinking about viscosity, right? So you start thinking about little rubber bands linking this layer to this layer. preventing this sliding, preventing one layer from sliding with relative to the other layer. And these little rubber bands are essentially a way of thinking about viscous forces. Okay, so this is one thing. So the presence of velocity shear is intimately linked with viscosity. Okay. If there was no viscosity, there would be no shear, in fact, because the layers would freely slide with respect to each other. Is the fact that there is viscosity in the fluid, in other words, there are these little rubber bands connecting the two shear layers, that is what gives rise to the phenomenon of shear itself. And here, if you're assuming a quasi-Keplerian disk, it has to have velocity shear. There's no way around it. A quasi-Keplerian accretion disk, there's azimuthal velocities look like this. So this is, since the r is in the denominator, at smaller r you have a larger v phi as compared to a larger r. And this is essentially velocity shear, like this, and you can transform it to something like this. Okay. Now, why is viscosity important for us? Because we know that apart from appearing in the momentum equation, viscosity also appears in the energy equation, right? Because viscosity is a dissipative process. Viscosity dissipates energy. The rate of dissipation of energy is something like this. That's the rate at which viscosity dissipates energy, where this is the coefficient of viscosity. Okay. Now, why is energy dissipation important? Because that's the whole point, isn't it? You wanted to transform, and what energy is dissipated? It's gravitational potential energy that's dissipated. You want it as large an m dot as possible. And where's the m dot coming from? It's coming from the gravitational potential of the central object. That's fine, but the ultimate observable is not the accretion disk itself. It's the photons that are emitted from the accretion disk. And why are the photons emitted? That's because the accretion disk gets hot. And why does the accretion disk get hot? Because there's viscosity in the accreting fluid which dissipates energy that heats up the fluid, and a heated fluid essentially emits photons, assuming there is a black body. Okay. So viscosity is central to not only the physics of the accretion process. If you had no viscosity, you would not have accretion at all. Okay. And it's also central to explaining the fact that the disk is luminous. Why is the disk luminous? Because it's hot. Why is it hot? Because viscosity dissipates energy. Okay. You can also look at the specific angular momentum. The specific angular momentum, which is something like rv phi. Okay, it goes as square root of r. In other words, larger radii have more angular momentum as compared to smaller radii. The larger radii rotate slowly, but they have more angular momentum as compared to smaller radii. That's what this is telling you. So matter has to lose angular momentum in order to accrete. And what causes it to lose this angular momentum? Viscosity. And viscosity also does another very important thing. It heats up the disk and makes it radiate, which is what ultimately makes the disk observable. So we'll stop here and we will consider the azimuthal component of the momentum equation when we start next. Thank you.